Recording.
Okay, welcome to EGR 445, Mechanical Engineering Systems. In today's class, we will continue the discussion from last lesson on spur gears. In last class, we talked about law of gearing. We talked about the basic need for the gear, advantages and disadvantages of gear train, and we looked at the transition from friction wheels to gears. Now, the first thing in today's class, we are going to talk about the nomenclature or the terms that are used in gears. So let's consider a pinion gear or a small gear and a large gear, which is called as gear. So you have a pinion and you have the large gear. Now, what we do is we cut teeth on these gears. So the pinion gear will have teeth and the big gear will have teeth. We talked about that these gear profiles will be of particular shape. So the gear profile will be either involute or cycloidal. Now, if you look at the way the force will be transmitted from the driving gear to the driven gear, the force will not be transmitted perpendicular to the line of centers. So if you think about, this is the center 1, this is the center 2, and I have this line which is joining these two centers. The force will be transmitted at an angle, and this angle is called as the pressure angle. So this angle is called as pressure angle. And this is the important difference between the friction wheels and gears. If you look at the friction wheels, so I'm just showing you two wheels that are in contact and they are transmitting the power, then the force that is transmitted will be perpendicular to the line of centers. But in the case of gears, that line is going to make certain angle, and that angle is called as phi, and this phi is the pressure angle. And pressure angle, so phi is equal to pressure angle. Typically, you would have 14.5 degrees or 21 degrees of pressure angle. And the reason for the pressure angle is, since we have this gear profile that has certain geometric relationship, if you were to draw the line of action of force that is being transmitted from the driving gear to the driven gear, you will notice it is at that angle. And pressure angle is one of the design parameters for the gear, which means whenever you are going to select the gear, you would specify the pressure angle. It is important to note that the pressure angle for driving gear and pressure angle for driven gear, they have to be the same. You cannot mesh of 14.5 degree pressure angle pinion with 20 degree gear. Now let's look at sort of the magnified view of the gear profile. So I'm gonna draw a couple of gear teeth. So if you look at this is a gear profile, and I'm just showing two teeth. So first and foremost, you will have a center at say O1. So there is a center here at O1. If you replace the gears in mesh with imaginary circles, the way we have shown here. So this is the gear pair, and these are the friction wheels. The imaginary circle that goes through the meshing line of the gear is called as the pitch circle diameter. So pitch circle diameter, and it is also called as PCD. Now pitch circle diameter is this imaginary circle that by purely rolling action will give you the same motion as the gear. So you can think about that this is the pitch circle. So this is the pitch circle for pinion, and this is the pitch circle for gear. This is the pitch circle for gear. In other words, these two pitch circles, they mesh at this location where the gear pair is coming in contact. Now, the pitch circle diameter is the diameter of this imaginary point. And the point where two pitch circles come in contact, which is same as the point where two gears come in contact, is called as the pitch point. So P is the pitch point. So this is the point where two gears mesh or two pitch circles match. Now, when you look at the gear tooth, so this is the pitch circle diameter. You have part of the tooth that is above the pitch circle. You have the part of the tooth below the pitch circle. So this radial distance is called as addendum. This radial distance, it's called as the dedendum. So this is called as dedendum. Now, it is very important to note that if you were to draw a circle that goes through all this tooth profile, so this is the first tooth, second tooth, all this tooth profile, this is called as the addendum circle. If you look at the dedendum, and if you look at the circle that encompasses this dedendum, this is called as the dedendum circle. Now, here is something important. The most important parameter in the gear, it's called as the module, which is called as M. This is the most important parameter in the gear. This is the ratio of the pitch circle diameter, PCD, divided by number of teeth. So I want you to remember this. For a gear, module M is a design parameter where PCD is the pitch circle diameter. If you divide that by number of teeth, you are gonna get a number that would have the same unit as the pitch circle diameter. So if your pitch circle diameter is in millimeter, your module is gonna be in millimeter. If your pitch circle diameter is going to be in centimeter, your module is going to be in centimeter. Now the next term is called as the circular pitch. So the circular pitch is distance over the pitch circle diameter around the PCD. So this is called as circular pitch. And circular pitch is nothing but pi times module. So circular pitch is pi times module. And this sometimes is used in design calculations. And you can see that circular pitch is nothing but the perimeter of the pitch circle diameter, which is pi d. So let me give you relationships. Circular pitch is nothing but pi times d divided by number of teeth. So this is the relationship for the circular pitch. Now, one thing that I want you to understand that the addendum and dedendum, they are related with module. Typically, the addendum is equal to one module. Typically, addendum is equal to 1 times module. Now, please understand, dedendum of one gear meshes with the addendum of the meshing gear. So which means dedendum will be addendum plus clearance. Dedendum will be addendum plus clearance. And this is very important because you don't want interference. So which means when the two gears are meshing, there is some teeny tiny amount of clearance between the face of the tooth and then the bottom of the gear. So that is something to keep in mind. The top part, this is called as face width. Typically, we use B as face width. And then there is something called as the total depth, which is the difference between, the total distance from the addendum all the way to the dedendum circle, which is nothing but this guy. So this is the total depth. This is total depth. And then there is something called as the tooth thickness, which is nothing but the width of the tooth measured along the pitch circle. So basically, this is the tooth thickness. And then again, when you look at the design, you will have additional design parameters like filler radii. So for an example, you can't have very sharp turns. So basically, you are going to have some sort of fillet radii just to reduce stress concentration. And then basically you have the top land, which is nothing but this guy, this is called as the top land, and so on. These are some of the important gear parameters. And when we try to design the gear, the most important thing is we determine what is the pitch circle diameter, what is the number of teeth for that gear. Essentially, we find the module. Once we find the module, almost all the dimensions are dependent on module. So just remember this, module is the very important parameter in gear design, and module is given as pitch circle diameter divided by number of teeth. Now, I want to talk about how do we design gears. Now, if you want to design the gear, the gear design is based on multiple considerations. First and foremost, you want to design the gear that is strong and does not break in bending. So which means if you apply the loading, the gear tooth should not fail. At the same time, the gear should be able to sustain the wear and tear that is occurring at the contact points. So basically, it should resist the surface forces and surface stresses that will cause that gear to wear out prematurely. Also, it should be able to withstand the fatigue loading, because please try to understand these two gears, they come in contact and they disengage, again come in contact, and this process is happening at a very high speed. So the loading on the gear is sort of a fatigue loading, and you don't want gear to prematurely fail in the fatigue. So one thing that we have to understand is we can design for one criteria and check for the second criteria. So, or we can design for the second criteria and check for the first criteria. So in this class, at least for the gear design, what we will do is we'll design the gear from the strength consideration and check the gear for the wear. And I will give you a recipe, a step-by-step approach to find out how to design the gear, how to find out the module, and how to solve gear design problem step by step. Now, one thing that we have to be aware of is the interference in the gear. And this is quite important. So, interference. In gears. Now, please understand that if you have very less, so if you have very few number of teeth, then what may happen is some teeth may not engage properly with the mating gear. So if you have a gear profile, there are restrictions on the minimum number of teeth that you should have. So for an example, let me talk about gear and minimum number of teeth. And there is a mathematical relationship, or there's an equation that depends upon the gear ratio and then the fraction of addendum. But instead of using that equation, we will use this empirical relationship. So if the gear is, for an example, 14.5-degree pressure angle composite, then the minimum number of teeth is 12. If the gear is 14.5 full depth involute, then the minimum number of teeth is 32. If the gear is 20 degree full depth, then the minimum number of teeth is 32. If the gear is 20 degree full depth, then the minimum number of teeth is 32. If the gear is 30 degree full depth, then the minimum number of teeth is 32. If the gear is 40 degree full depth, then the minimum number of teeth is 32. If the gear is 50 degree full depth, then the number of teeth is 18. And if you have 20-degree stub, then you stub involute, then this gear is going to have 14 number of teeth. Now, I just want to talk about what do we mean by a full depth involute and what is a stub involute. So full depth involute is the gear tooth that has the full involute profile, something like this. But sometimes, because of the design consideration, you can have sort of a shorter gear, something like this. This gear does not have the full involute profile, but it is sort of shaved off at the top. That profile is called as the stub. And I want you to note the difference between the full depth and the stub. So for an example, if you have full depth profile, then basically you are going to have more number of teeth. If you have a stub profile, you are going to have less number of teeth, because by shaving off the top of the gear, you are reducing the possibility of interference. The other thing is materials. Gear materials can be all the way from metals like steel, aluminum, cast iron, all the way to non-metals like plastic, nylon, and some sort of exotic materials like carbon fiber. And it completely depends upon the characteristics that we want. So for an example, depending upon what wear characteristics we want, what the strength characteristics we want, what is the size of the gear, what is the operating range of the gear, what is the use of the gear, what is the duty factor on the gear. So there are different materials. And I just want to point out the properties for different gear material. They are given in table 28.3 on page 1035. So if you look at the gear properties, you will have something called as the material. Then it will talk about the condition. And this condition is basically the heat treatment. Then you're going to have BHN, which is nothing but the Brinell hardness number. And this talks about the surface hardness. And then it will talk about the strength. And this strength is usually given in Newton per millimeter square. And the idea is we select a combination of hardness and strength. We select a particular combination of hardness and particular combination of strength, so that our gear profile and our gear is able to withstand the load and operating conditions in practice. And if you look at the materials, you are going to see the materials all the way from cast iron. There are different grades of cast iron. And again, with different grades of cast iron, there is different heat treatment. And as you change the heat treatment, the surface properties such as hardness changes. So that is something to keep in mind, all the way to alloy steels, which have excellent strength properties and good hardness properties, all the way to chromium molybdenum steel, all the way up to phosphor bronze, case hardened steel, and depending upon the applications, for an example, size, weight, cost, then whether we have lubrication available or not, what is the level of heat that needs to be dissipated, you select the appropriate material. So let's talk about how do we design a gear. So some of the design considerations. So how do we design a gear? And we will, when we look at the problems, we will go step by step in design considerations, and we can have a very loose open-ended specification like design a power transmission gearing to transmit 10 kilowatts at certain speed ratio. So at that time, we have to choose the appropriate material, we have to choose the appropriate heat treatment, we have to choose the service factors, and we have to look at the operating conditions. We have to make some assumptions and then start with a basic skeletal design and make sure that that design is safe in all possible operating conditions. If that design fails at certain point, we have to go back and revise the design. But some of the main design considerations is first, the power that needs to be transmitted. So for an example, if the power transmission is small, then you could potentially use a gear profile or gear that is made up with cast iron or aluminum without any special treatment. If the power transmission requirement is high, then probably you have to go to a phosphor or the manganese steel or a molybdenum steel or nickel chromium steel that has excellent power transmission capacities, high strength, and it is hardened and tempered. Then next thing is the speed, because why speed plays an important role? Because if you look at the high speed power transmission, if you have high speed, the fatigue loading is going to be higher. That means the gear will be loaded and unloaded faster. So that is very important. The next consideration is something called as the velocity ratio. So what is the ratio of the velocity? What is the reduction? Velocity ratio. What is the gear ratio that we want this gear pair to have? And last but not least is the center distance. And the center distance is important because that dictates how far those two gears should be, the module, then basically the radius. So center distance for the spur gear is radius of the pinion plus radius of the gear. So, and as you know, the radius of pinion and radius of gear is dependent on module multiplied by number of teeth on pinion divided by 2, module number of teeth on gear divided by 2. So center distance dictates the module. So the design, this center distance is important consideration. And one thing I want you to note is I'm denoting TG as the number of teeth on gear. So TP is number of teeth on pinion, and TG is equal to number of teeth on gear. And also we need to make sure that the gear is strong and also able to sustain the wear. So the gear should have enough strength so that it does not fail in bending or under the dynamic loading, and it should be strong enough so that the surface does not pit or there is no material removal on the surface because of the wear. And then we have to ensure that the gears are properly lubricated. The gears are they should not deflect a lot more than necessary. Otherwise, if the gears deflect, then there is and it leads to permanent deformation. Then the gear profile would lock, and all those things are not good for continuous power transmission. Now, let's talk about the design of gear based on the strength criteria. So design of gear based on strength. This is also called as sometimes beam strength. And this leads to something known as Lewis equation. So fundamentally, this principle is simple. If you look at the gear profile, and I'm going to show this gear profile, a very simple gear profile. Then what you have is you have a tangential load on the gear, and I'm going to call this WT. WT is the tangential load. Then you have something called as the normal load. So WN, which is the normal load. And you have something called as the radial load. Now let's try to understand what are these different types of loads. So going back to our power transmission, say if I have a pinion and if I have a gear, if I have a pinion and if I have a gear, and my tooth engagement is somewhere here. So this is where the engagement is taking place. We talked about the gear force is transmitted along the pressure angle. So for an example, say this is the pressure angle. This force is actually Wn. And if you look at Wn, this Wn force can be resolved into two components. One component, so if you look at Wn, there are two components. One component is the tangential component, and the other component is going to be the radial component. So Wn is equal to square root of Wt square plus Wr square. Now the next question is, then how do we find out these values? So first and foremost, Wn is the force that is transmitted from the pinion to the gear, or from the driven gear to the, or from the driving gear to the driven gear. But if you look at the force that is causing the torque to transmit, so if you think about it, this is nothing but the pitch circle diameter. So this is PCD. So Wt multiplied by the radius of the gear is gonna give you the torque that is transmitted. So if you look at the torque is equal to Wt multiplied by the radius of the gear. Now what I want you to do is, for a second, consider that this gear profile is like a beam, and this Wt is causing this beam to bend. So looking at, and that's why this word beam strength comes in the picture, because what we assume that this gear profile, this gear is sort of a cantilever beam. So we are going to assume gear as cantilever beam. And this is an approximation. And what we will do is we will modify this approximation as we go through the process. So I'm going to find out sigma bending, and I'm going to just call this sigma W, is M, which is the moment multiplied by Y divided by I. So this is nothing but the bending stress on the gear. Now, M is the bending moment, and let's assume this height from here to here. Let's assume this height to be equal to H. So the bending moment is going to be Wt times H, where Wt is the tangential load and H is nothing but the length of the tooth. Now Y is equal to half of the section profile, which is given as T divided by 2. And I is the moment of inertia, and moment of inertia for a rectangular section is given as BD cube by 12. And for this particular gear profile, let me give you one more dimension. If this dimension is B, I want you to focus on the dimension B and the dimension T. So this dimension is T. I want you to consider the beam of width B and thickness T. So the value of I is going to be B times T cube divided by 12. And just to give you an approximate understanding, so think about it. This is just the basic approximation. Think about it like this is the beam. Wherein this is T and this dimension is B. And clearly, this tooth profile is not rectangular, so we need to take into account. But assuming just the basic rectangular profile, we have BT cube by 12, and that is causing this tooth to bend. Now, substituting all these values, sigma W is going to be Wt multiplied by H, T by 2 divided by BT cube by 12 is equal to WT times H, and then 1/2 12 goes out, you get 6 divided by BT square, and that gives me WT is equal to sigma W times B multiplied by T square divided by 6 multiplied by H. So this equation is the equation for determination of WT when we know the bending strength of the beam. Now clearly in this equation, the value of H and T, they completely depend upon the gear profile. So if you look at H and if you look at T, they are dependent on the gear. Now, if you make certain assumptions, something like, and this is an assumption, if you think about T is equal to X times PC, which is the circular pitch, and H is equal to another factor K times PC, where PC is the circular pitch, what happens is this equation can be simplified all the way to WT, which is the tangential load, is equal to sigma W times B multiplied by X square PC square divided by 6K PC. And this equation leads to, this is important, sigma W multiplied by B, which is the face width, multiplied by the circular pitch, multiplied by a factor, which is X squared divided by 6K. And this entire equation can be now written in a very simple form. And this is the equation that we are going to use when we try to solve the gear design problem, is sigma W multiplied by B multiplied by PC multiplied by Y. This guy is considered as Y, where Y is known as Lewis form factor. Form factor. And this is just a number. Now, as you know, PC is the circular pitch that can also be expressed as pi times module. So this can also be substituted in this equation. And now your equation is going to be WT is equal to sigma W multiplied by B multiplied by pi times M multiplied by Y. And that is the fundamental equation that we will use in the gear design. And this gear design is based on the beam strength, because we assume the gear to be a cantilever beam, and then we try to find out the bending stresses. Now, how do we find out the value of Y? Now, to find out the value of the Y, we need to find out this relationship X squared divided by 6K. And for different profiles, different gear profiles, that relationship has been worked out, and we know the expression for Y. So I'm going to write this equation down because this equation is very important. WT is equal to sigma W multiplied by B multiplied by pi times M multiplied by Y. And I just want to give you the units. This unit is Newton per millimeter square. This is in millimeter. Pi is dimensionless. This is in millimeters. So finally, Wt is going to be in newtons. So please note, Y and pi are dimensionless. So let me give you the expression for Y. This expression is dependent on the type of gear. So for an example, if you have a 14.5 composite or full depth involute, so this equation is given as 0.124 minus 0.684 divided by T. And we are not expected to remember this equation. You will use or refer to this equation in the design data book, or this equation may be given to you in the problem. So this is the equation for 14.5 composite and full depth involute. The next expression, if you have a 20 degrees full depth, which is 0.154 minus 0.912 divided by T, where T is the number of teeth. This for 20 degrees full depth involute. And the last is 0.175 minus 0.841 divided by T for 20 degrees stub gear system. So when you start designing the gear, first you have to decide whether you are going to use a 14.5 pressure angle or a 20 degree pressure angle. And again, it depends upon the application. And design data book will give you some guidelines on how to choose particular pressure angle or what is the common practice on the pressure angle. Then you have to see whether you are going to use a full depth or a stub gear system. And once you make this determination, you can find out the value of Y, and then you can use the equation for a beam strength, which is Wt is equal to sigma W multiplied by B multiplied by pi multiplied by M multiplied by Y. Now, this needs a little discussion. So sigma W is actually called as the working stress. So sigma W is called as working stress. Now, as you know, that the gears is a complex system because it again depends upon the velocity at which the gear is acting. So because if you have a gear profile or a gear that is rotating at low speed, and if you have a gear that is rotating at high speed, the level of fatigue loading on the gears is going to be different. So clearly the working stress for the gear that is rotating at slow speed will be different than the working stress for the gear that is rotating at high speed. So this working stress, sigma W, that is used in this equation, sigma W that is used in this equation is dependent on the velocity. So this is given as sigma O multiplied by Cv, where sigma O is allowable static stress. So this is commonly the stress that we are aware of. So for example, when we use the mechanics of material equations, we assume the loading to be static or quasi-static. Then the load or the stress equation that we used to find out the stresses in the stress strain curve or in experiment, that is sigma O. But this needs to be multiplied with something called as the velocity factor, because the strength of the gear is dependent on at what speed the gear is rotating. So this is called as the velocity factor. And velocity factor is given by equation, and I will give you the equation Cv. You don't have to remember these equations. These equations are given in design data book. So if the gear profile is, or the gears are rotating at slow to medium speed, and the gears are ordinarily cut, which means they are not precision made, which means there will be more vibration and more noise. So the Cvs factor is given as 3 divided by 3 plus v, where v is the pitch line velocity, which is pi dn by 60. So this is the diameter and this is the speed in RPM. And it doesn't matter whether you choose the pinion or the gear, the pitch line velocity, v is called as the pitch line velocity. Pitch line velocity is going to be the same. So this is nothing but this velocity. So the pitch line velocity is going to be the same. So the equation is 3 divided by 3 plus v for ordinary gears, and where the velocities is up to 12.5 meters per second. So if you have a gear that is rotating at maybe 10 meters per second, this is the velocity factor that you will use. If your gear is carefully cut, which means it's more accurate, less vibration, less noise, less dynamic variation in the load. So this is given as for carefully cut gears. If you have super duper accurately cut gears and V is less than equal to 12.5. If you have super duper accurately cut gears, then the equation is 6 divided by 6 plus V for accurately cut gears, and V is less than equal to 20 meters per second. And in certain cases, if you are going to use the plastic gears or some sort of non-metallic gears, CV value is given as 0.75 divided by 1 plus V plus 0.25 for non-metallic. And what we will do is we'll take multiple examples. We'll look at different types of gear profiles. We'll look at different types of gear trains, how they are used, and in that case, what CV to use, that will be clear. Now, the next question is, how do we find out value of sigma O? Now, and this is an important question. So, sigma O. How do we find out the value of sigma O? Sigma O is given as allowable static stress. And allowable static stress is nothing but the yield stress in the case of ductile materials and the ultimate stress in the case of brittle materials. Because if you look at the stress strain curve for the ductile material, you have the yield point, stress divided by strain. If you look at the brittle materials, they don't have yielding, they just have failure. So you have stress divided by strain. This is for ductile and this is for brittle. Now, but for commonly used gear materials, the values of allowable static stress are given on in table 28.4 on page 1039 of the text. I'm going to list some important materials that are commonly used and their values of sigma O. And again, this is just a guideline. You will notice in certain materials, the range is quite wide because it also depends upon the type of heat treatment, then the type of cooling, normalizing, annealing, that all affects the material properties. So we have to use the design data book. But for an example, for if we are going to use cast iron, which is a brittle material, so this is Newton per millimeter square. Typically, cast iron gears are used for low power transmission. This is about 56 to 60 Newton per millimeter square. Now, if you look at the carbon steel, and please understand when I say carbon steel, you can have a low carbon steel, you can have a medium carbon steel, or you can have a high carbon steel. And the properties, because of the carbon content, are different. But in general, for a forged carbon steel, it's a ductile material, which is about 120 Newton per millimeter square. Now, in certain cases, if we go with special purpose alloy steels, you can go all the way up to 350 Newton per millimeter square. If you go to maybe Prosper bronze, then you can go up to about 84. And for each material, there are different applications. Sometimes we have to use sort of non-metallic gears. So say plastic or maybe bakelite, so or Delrin. So in that case, typically for example, bakelite, the gears could have, this is for non-metals, you can use about 56. And many a times what we do is we just look at the design data book or machinery's handbook and then come up with design loads. Now, in certain cases, when the design load is or design stresses are not known, what we can do is it's okay to make reasonable approximation and proceed with the gear design. So for an example, if the gear material is not specified, but you see that the power transmission requirement is high, then there is no harm in going with alloy steel as a material to design the gear. Since alloy steel has high sigma O, then the size of the gear is going to be less. So sigma O is found out from the design data book. And once we find out the design data sigma value of sigma O, that needs to be multiplied by the velocity factor, and that is used as the key parameter in Lewis form factor equation. Now, the next thing is, and this is super important, is if you look at the gear is loaded, always loaded under dynamic load. It's under dynamic load. So even though we are looking at the beam strength design and other stuff, but it is actually always under dynamic load. So what we want to do is we want to come up with some sort of estimate of dynamic load. And it's very difficult to determine the dynamic load because the dynamic load, it's changing, and it also depends upon the gear profile, or whether the gear is new or old, whether you have lubrication or not, how much deflection, if the gears are vibrating or not, if the gear is accurately cut or it's not properly cut, or if it is has some irregularities. So basically, the dynamic load on the gear is dependent on a lot of factors that is not possible to measure accurately. So what we do is we try to sort of estimate this dynamic load based on the factors that we know either experimentally or using empirical relationships, and we assume this dynamic load to be dependent on the pitch line velocity, the face width, the material, accuracy, and then basically what we do is we come up with an approximate relationship for this dynamic load. And we don't need to derive this, but the way we find dynamic load, WD, is called as the dynamic load that is given as WT. And please note, WT is the tangential load plus 21V multiplied by B multiplied by C plus WT divided by 21V plus square root of BC plus WT. Now this equation is called as Buckingham equation. This equation is called as Buckingham equation. And this equation actually comes from experimental results, empirical results, and dimensional analysis. So, but let's look at the terms in this equation. WT we know, which is the tangential load. V is nothing but the pitch line velocity. So V is the pitch line velocity. V is the pitch line velocity. And it is important that this velocity has to be in meters per second. So if you have pi dn by 60, you have to make sure that this d, which is the diameter, is in meters, and this n is in RPM. So V is the pitch line velocity in meters per second. Now B, which is the face width, B, which is the face width, that has to be in millimeters. The face width has to be in millimeters. And C is called as the deformation factor. This is called as the deformation factor. And this deformation factor, and it is very interesting to know, is in Newton per millimeter. This deformation factor is given in Newton per millimeter. So what I want you to do is, I want you to try to plug in these values. You will notice that this B is in millimeters. This value of C is in Newton per millimeter. So this product is gonna give you in newtons. So WT must be in newtons here. So WT has to be in newtons here. But velocity is going to be in meters per second. Now, deformation factor is dependent on how the tooth is cut. So deformation factor is related to the manufacturing of the gear teeth. And I would encourage you to go on to YouTube and watch how gears are cut. So how gears are cut. So if you go to YouTube, you will see very nice videos of gear cutting machines. And it's basically the gears are cut sequentially. So you have a specific cutter, and on that cutter, you have something called as the error in action. Now, what that means is basically the amount, it's sort of a tolerance on the gear, a gear cutter. So depending upon what type of error in action you have, depending upon the form of the gear that you have, and depending upon the material that you have different values of C. Now, there are two ways to find out C. So let me give you the tabular approach first, and then we will talk about the equation approach. So if you look at the table, which is table 28.5 on page 1040, if you look at the table 28.5 on the page 1040 in your textbook, you will see this table where you have the material, and this material gives you sort of a pair. So you have a pinion and you have the gear. You have the pinion and you have the gear. And then you have the pressure angle. And then you have the tooth error action. So I will just write error in action. And this error in action is usually given in millimeter. That is related to the tolerance of the gear cutter. And this error in action, depending upon the type of gear cutter you use, could go from 0.01 all the way to 0.08. And then for particular combination, say for an example, let me give you an example. If you have a steel pinion, and then you have say cast iron gear, and you have 14.5 degrees of pressure angle, your C value, this gives you the value of C. For 0.01 error action is 76, and 0.08 error action is 608. So as you can notice that the value of C, which is the deformation factor, is very much dependent on the type of cutter that we are going to use. You can think about it like if our cutter is quite accurate, or if our tolerances are super good, very well controlled, then our deformation factor is going to be low. If our cutter is worn out, or if it is has more tolerances, then our deformation factor is going to be quite high. And what does it mean to have a high deformation factor? Clearly, when you have a high deformation factor, the total dynamic load on the gear is going to be higher. So again, there is a sort of a balance that you have to maintain. Alternatively, you can actually use an equation. And find out this value of C, the deformation factor, based on the materials of the gear and material of the pinion. So alternatively, and there is no preferred approach. I usually go with the tabular approach, but you are welcome to use this equation approach, which is given as K times E divided by 1 divided by the Young's modulus of pinion plus 1 divided by Young's modulus of gear. Now, if you think about this variational or difference in Young's modulus is sort of indicative of the relative strength. So what we want to do is we want to see if the gear is meshing with the pinion, which is equally strong or which is weaker, and that information is kind of captured in this Young's modulus. So K, again, this is the factor depending upon the tooth form. So this is also called as the factor depending on tooth form, and this is also related with the type of cutter. So for an example, if you are going to have 14.5 full depth, usually the value of K is 0.107, which is 14.5 full depth. If you have a 20-degree full depth, this will be 0.111 for 20-degree full depth. And if you have a stub gear profile, this will be 0.115 for 20-degree stub. And again, this error in action E is the error in action. So here you can actually specify what would be the error in action on the cutter, what are the tolerances on the cutter, and then you can find out the values of C. Again, it's totally up to you. Now, depending upon this, again, this E value typically is not chosen randomly. So for example, I give you a sort of a logic behind the error action. If the gears are going to rotate slowly, if the speed is low, then you can allow gears to have more error. It's not going to affect the performance very much, because finally, if you look at the dynamic load, you have the velocity that is multiplying the deformation factor, which depends upon the error in action. So if the gears are rotating at slow speed, then perhaps the higher error in action is okay. If the gears are rotating super fast, then clearly what we need to make sure is our gear cutter tolerances are very tight. So we can't allow a lot of error in action. Also, when the gears are small, then again, depending upon are we cutting the small gears or we are cutting the large gears, this error in action also is dependent. For example, for small gear, error in action is less. For large gear, error in action increases, because it's clear that when we're trying to cut the large gear, the possibility of making tolerance errors or tolerance stacks is quite high. So this error in action depends upon whether we are going to have a gear pair that is rotating at low speed, or gear pair has a high pitch line velocity, and what is the module. So if you look at the textbook, there are two tables. So table 28.6 gives you the relationship between the pitch line velocity and error in action, and table 28.7 gives you the error, the relationship between the module and error in action. Now, there is a fine balance. So sometimes when we design the gears, we have to go back and forth and select the appropriate value of error in action and perform this calculation. But I'm gonna take a break here for 15 minutes and we will continue this discussion at 7:30. Okay, so let's continue our discussion. So you can look at table 28.6, and this table is on page 1042. No, sorry, 1041. So these pages, I mean, these two tables are on page 1041, and you can use these tables to find out the value of error action. And depending upon whether you have commercially cut gears, carefully cut gears, and precision gears, the values of error action, in other words, the tolerances, are different. And this will be clear when we take an example when we look at actually the gear design. So the next important point that needs a careful consideration is something called as the static tooth load. And this is important consideration. So static tooth load. Now, why this static tooth load is important? Because if you think about it, all the discussion on the gear started with a simple approximation, and that simple approximation led to Lewis form factor equation and the beam strength. Now, but what we want to make sure is the gear is not only safe under so-called static loading, but the gear is also safe under something called as the fatigue loading. Now, what does it mean? It means, let me look at the equation that we derived first. So WT is equal to sigma W multiplied by B multiplied by pi multiplied by M multiplied by Lewis form factor. And this equation we derived here somewhere. Yeah, here. So sigma W multiplied by B, PC is pi times M multiplied by Y. But this equation uses sigma W. And where is this sigma W coming from? Sigma W is nothing but sigma O, which is the static, allowable static stress multiplied by the velocity factor. Now, if I want to look at the endurance strength of the gear, now this is very important. Since the gear is loaded under fatigue loading, as gear is loaded in fatigue, because it's continuously engaging, disengaging, engaging, disengaging, I want to find out something called as static tooth load. In this equation, this sigma W is replaced by sigma E. And all other equations, all other parameters remain the same. All other equation parameters remain the same. Only difference here is sigma W in the Lewis form factor equation is replaced by the endurance strength. So this is the endurance strength. And for different materials, you would have different endurance limit. So where do we get this endurance limit? So there is a table. There are a lot of tables that we need to refer to. So there is a table 28.8 on page 1042 that gives us the values of endurance limits. And one thing I want you to understand that steel can be heat treated, which means what you can do is you can heat the steel and cool the steel at different cooling rates, and that would change the surface hardness. And that change in the surface hardness will affect the endurance limit. So what you want to do is, if you look at this table, it talks about material, the Brinell hardness number, and the value of sigma E. Now, if you look at the materials such as cast iron, typically the BHN is going to be about 160 BHN, which is moderate to low, and sigma E is 84. However, if you look at something like steel, since steel can be heat treated, the Brinell hardness number can go from 150 all the way to 400. And with that, you can have the endurance limit going from 250 megapascals or 250 Newton per millimeter square all the way to 700 Newton per millimeter square. So the megapascal, which is same as Newton per millimeter square. So what it means is when you are looking at steel, you have a wide variety or wide choice that is available. And this is very nice because if you decide to go with the steel gear and pinion, we can actually recommend, or we can dictate, or we can suggest particular hardness number, and that for that corresponding hardness number, there will be something particular value of WE. Now, one thing that we need to make sure is this static tooth load. So static tooth load, which is WS, must be greater than WD, which is the dynamic tooth load. Now, let me explain the rationale behind this condition. So if you look at the dynamic tooth load, this dynamic tooth load comes from WT plus a factor which depends upon the velocity, then the deformation factor, then face width, and so on. So this is the maximum possible load. This is sort of the maximum possible load on the gear. And static tooth load is nothing but the strength of the gear. So this is nothing but the strength of the gear. What that means is, depending upon the material that I choose, depending upon the hardness that I specify, my sigma E is going to be different. So I want to make sure that my strength or the ability to withstand load is greater than the maximum possible load that is coming on the gear. So that is the condition that must be checked. So our gear has to be, the gear static tooth load has to be greater than dynamic tooth load. But if you look at this condition can be satisfied uh, by multiple ways. It's a design problem, so there is no right or wrong answer. So for an example, what I can do is, if I see for some reason the dynamic load is very high, then what I would do is I will choose the steel, but I will recommend the Brinell hardness number of 400. Clearly, this requires a significant amount of heat treatment, but that gives me a very high value of sigma E, or the endurance strength is very high. So I can make sure that my static tooth load is greater than the dynamic tooth load, because the dynamic tooth load is basically coming from the loading conditions. So this is because of the loading condition. And the static tooth load, it comes from the basic design specifications. So what I can do is I can adjust my design specifications in such a way that my gear can meet all the possible loading conditions that could exist in that power transmission. So this is a condition that must be checked. Now, the last part, and again, this is something super important. The last part is looking at the wear tooth load. So wear tooth load. Now, wear tooth load, it means that is the maximum possible load that the gear is capable of carrying. So the wear tooth load is the maximum load that the gear can carry. And this wear tooth load depends on different parameters. For an example, the face width, the pitch circle diameter, uh, the, the ratio factor, the velocity ratio, load stress factor, and so on. But I just have to give you sort of some idea on where is this wear tooth load is coming from. So what I want you to do is, I want you to assume that you have a force that is acting on this surface. You have this force that is acting on this surface. So if you look at the amount of stress under the load, if you look at the stress here, the value of stress is going to be significantly high, which means if you follow the stress pattern around the point of action of load will show something like this. The stress wave or the stress lines, they disperse as you go away from the load. What it means is there is very high localized stress. And please note that when we are designing a gear, actually the gear load is transmitted along the line. So there is always a line contact between two meshing gears, which means there is going to be very high localized stress over there. And these high localized stress can possibly give rise to fracture and material separation. So these high localized stresses can actually cause fracture. But there is something interesting about this fracture. This fracture is in the form of small elements, microscopic elements of the material being separated. That's why you will observe that when you have gears in contact, you will notice that the surface looks either super shiny or it looks pitted. And the reason for that is this small material elements, they separate out from the surface. So we want to make sure that our gear profile is safe under this high stress loading. And for that, what we calculate is something called as WW. And this WW is nothing but the maximum load or the wear load, maximum wear load or load that gear can sustain without premature wear. And again, this also is a function of the type of lubrication that you have, the how surface is treated, and so on. But a general expression is given as dP, which is nothing but the diameter of the pinion multiplied by B multiplied by Q multiplied by K. Now, dP is the diameter of the pinion. And why do we use diameter of the pinion? Because if you think about it, gear, you have gear and you have pinion. The pinion will have smaller diameter, and that will give you less or the lower value of maximum load. So we want to make sure that this lower value of maximum load is greater than the dynamic load. So this B is the face width of pinion. Q is the ratio factor. And K is called as the load stress factor. And it may seem that the gear design is sort of complex, but it's really not. I will give you a step-by-step recipe, and that will make our life very simple. So this Q, which is called as the ratio factor, it depends upon the velocity ratio. So this ratio factor is given as 2 times the velocity ratio divided by velocity ratio plus 1, where VR is velocity ratio. And this equation is for external gears. Now, if you have an internal gear, then same equation, only thing is the denominator changes. 2 times velocity ratio divided by velocity ratio minus 1 for internal gears. Which means if you have the gears that are like this, then you would use external. And if you have the gears wherein you have an annular gear and you have a gear which is inside, then you will use this equation. And this VR, which is the velocity ratio, is again nothing but the reduction ratio or this is nothing but simply the ratio of number of teeth on the gears divided by number of teeth on pinion. So this ratio will always be greater than 1 or equal to 1. So please note the number of teeth on the gear will be greater than number of or equal to number of teeth on the pinion. Now let me spend some time on what is this load stress factor. This load stress factor is basically the function, this load stress factor, this depends upon pressure angle, endurance limit, and the Young's modulus, E. Now, this is something interesting that we need to spend some time on, because the hardness dictates the endurance limit, and endurance limit dictates the hardness, and both these together dictate how much of wear strength the gear has. For an example, I just want to give you a simple understanding. Think about it like if you have a surface that is hard. So assume that this surface is quite hard. So this is sort of hard, which means it will take more load uh, than a soft surface. So basically, that's why what we do is we have some special surface hardening treatments, or we have short pinning, or we have additional carburization, heat treatments that would make sure that the surface hardness is high, that would improve the wear characteristics of the gear pair. This value K is given as sigma ES square sine of phi, where phi is the pressure angle divided by 1.4, and then you have the Young's modulus for the pinion plus Young's modulus for the gear. So you have sigma ES, and this is something important. Sigma ES is the surface endurance limit. In Newton per millimeter square. And I just want to caution you that this surface endurance limit is not same as the endurance limit that we used in the strength calculation. So a word of caution. So be careful here. This is different than this guy. So I just have to note here, sigma E in WS is different than sigma ES in WW. So please remember this. And I will explain to you why they are different. Now, if you look at the endurance limit, so difference between endurance limit and surface endurance limit. So what I want you to think about is you have a shaft, and this shaft is maybe carburized, which means you impregnate or you stick this rod or shaft in carbon, heat it so that the carbon gets diffused, and then you have a high carbon content at the surface. So this is called as carburization. Then you heat it, and then you actually perform a heat treatment. Now what happens because of the heat treatment? The surface hardness is higher than the local hardness. So this is case hardened. And then here you have a different hardness. So I'm just going to give you an example. Say you have 250 BHN. BHN is the indication of hardness, which is called as the Brinell hardness number. And here, say because of the carburization, you have 400 BHN. Now the endurance strength is dependent on the hardness. So what it means is sigma E, which is in the core, is different than sigma ES that you have on the surface. Now what does that imply? Now I want you to look at the failure because of the strength. So when you have a failure because of the strength, this whole piece is resisting that failure. But if you have a failure because of the wear doesn't start at the core. So the failure in the core is because of the strength failure. Say maybe you add very high amount of load, and then because of that, this shaft bends, and then you see that the core load or the load at the center is very high. But typically, the wear is going to start at the surface. This is where the wear initiates. And this is the point of failure. So if you think about it, the wear resistance is dependent on sigma ES. So wear resistance depends on sigma ES, but the beam strength or the core strength depends on sigma E. So that's why we use two different values for the wear. So that's why this gives us WW and this gives us WS. Nevertheless, idea is the same. This WW and WS, they have to be greater than WD. So WW has to be greater than WD, which is the dynamic load because of operation. And WS has to be greater than WD. But WW is related to the wear resistance on the surface, and WW is basically the core strength. So this is sort of the surface. If I were to say this is for the surface strength, and this is sort of the core strength. Now, how do we find out the value of sigma ES? And again, for sigma ES, you have another table. So if you look at the table 28.9 on page 1040, you have the material, then you have BHN, and you have the surface endurance strength. Now, there is an interesting question at this point, that what if I use sigma ES is equal to sigma E? What if I use this approximation? And to be honest with you, there is nothing wrong with this approximation. So what you are going to say is, there is no surface treatment. Whatever is the value of the core hardness, the same value you have at the surface. But typically, this may work out for low power transmission, but it may not work out for high power transmission. So for an example, if you look at cast iron, you have BHN, which is the surface BHN of 160, sigma ES is 630. If you have steel, and again, steel can be heat treated, you go all the way from 100, you go from 150, you can go from 150 to 400, and you have 350 Newton per millimeter square. And what I want you to do is, I want you to make a mental note. Sigma ES comes from table 28.9, and sigma E comes from table 28.8. So I want you to make a mental note of this, that sigma E is responsible for beam strength, sigma ES is responsible for wear resistance, and these two tables are next to each other, but these tables are different. So what are the major failure modes in the gears? So if you observe a gear, what are the major failure modes? So gear could actually fail in bending. Gear could fail in surface material removal, which is called as pitting. Gear could fail in large chunk of material removal and because of the heat, which is called as scoring. Gear can fail in abrasion, and gear can fail in corrosion. And each of these is related again to the amount of load, speed, type of lubrication, type of design consideration, operating point, the speed, the material, and so on. So these are the primary failure modes. And typically what you will notice is when the gear is going to fail, initially it will start wearing out, then it will become noisy, and after some time you will see that the gear shifting or gear transmission is no longer smooth. When the gear transmission is not smooth, the law of gearing is obviously not satisfied, and that leads to inconsistent velocity ratios, which means you are not going to get a consistent output from the gear train, and then that gradually will lead to the failure of the gear train. Failure of the gear train could be a physical separation of the tooth, or it could be noisy or very inefficient power transmission. So it's always a good idea to sometimes look at the gear, uh, understand the type of noise, look at the noise signature, vibration signature, and then decide whether that gear needs to be replacement or not. So this is sort of the theory that we discussed. Now let me give you the design process. So gear design process. Now this is similar to all the designs that we have looked so far. I'm going to give you a step-by-step gear design process. So typically the problem will state something like the power transmission requirement in kilowatt would be given. Sometimes the center distance could be given. Sometimes the velocity ratio could be given. Sometimes the material could be given, or material can be selected. Material known or to be or to be decided, TBD. So here, so and again we will work out 2 or 3 problems with different flavors. But step 1 is first and foremost we need to find out the tangential load. Step 1, WT. And how do we determine WT? There are multiple ways that WT can be determined. So let's start with first the power equation. Power is 2 pi T divided by 60. Typically, this value of speed will be known. So from that equation, we can find out the value of torque. So torque in Newton meter can be found out. And from torque, we can find out the value of Wt is equal to torque divided by the radius of the gear. And with this, we can find out Wt. Alternatively, if we know the values of the diameter, we can find out the pitch line velocity, pi dn by 60, where v is the pitch line velocity, where d is the diameter, n is equal to speed, and I say P is equal to power. And I can find out Wt is equal to power divided by V multiplied by Cv. So this Cv stands for the velocity factor. And we looked at the velocity factor. So you can find out Wt design, which is same as Wt. So let me make this small change over here. So you will multiply this by Cv. So you can use either equation 1 or you can use equation 2 and find out the value of Wt. Now, sometimes you have to kind of go back and forth in design, because this is a chicken and egg problem. Hey, we don't know what is the size of our gear, and we are trying to find out the velocity factor, because recognize that the velocity factor Cv is dependent on the pitch line velocity. And sometimes if we don't know the diameter, we may not know the pitch line velocity. So there is some trial and error that needs to be done. But once we solve one or two problems, you will see that we can go back and forth and determine the value of Wt. Now, to find out Cv, which is the service factor. So service factor, oh, sorry, I made a mistake here. This is not Cv, this is Cs. This is Cs. This is service factor. This is not Cv. I made a mistake. This is Cs. Cs stands for service factor. Velocity factor comes next. This is not a velocity factor. Please note, it's a mistake. This is a service factor. So what does it mean by service factor? Service means whether it's a steady operation, whether it is intermittent operation, it's heavy duty, heavy operation, and then is it going to be, say, 3 hours, or is it going to be 8 hours, or is it going to be 24 hours? So what type of duty cycle that system or that gear pair is subjected to? And the service factor Cs is given in table 28.10, which is on page 1045. So this service factor is kind of tells us that it's like an overloading factor. So when we design what type of duty cycle we expect this gear to sustain. So how much of overload can we expect this gear pair to sustain? The next step, step 2, is determination of gear dimension, specifically module. So determination of module, which is M. And module is the most important design parameters in gear. A quick recap: module is equal to the pitch circle diameter of the gear divided by number of teeth. So if you look at this, this is WT is equal to sigma W multiplied by the face width multiplied by pi multiplied by m multiplied by the value of y. So once again, B is the face width. This is module. And this is Lewis form factor. Now, I want you to understand the face width and the module will be same for the gear and pinion. So B and M. B and M will be same for pinion and gear. However, I want you to look at y. Just to give an example, if you look at the value of y, this value of y depends on the number of teeth, and number of teeth on the pinion and number of teeth on gear are different. Just to give an idea, so if you look at a 14 and a half composite involute, this is 0.124 minus 0.684 divided by t. So this t is going to be different for pinion and gear. So what it means is I want you to look at this equation. WT is equal to, and I'm going to write this equation slightly differently, sigma W times y B pi and m. This guy will be different for pinion and gear. So which means the product of sigma W multiplied by multiplied by y is going to be different for the gear and the pinion. Now assume the case that the gear and pinion are of the same material. Gear and pinion are of the same material. In that case, pinion is always weaker. So we can actually start, or we can actually design the pinion, because we always design the weakest element. So we always design the weakest link. So pinion is weaker. But now I want you to consider a case that the gear and pinion are of different material. So first we need to decide whether the pinion is weaker or the gear is weaker. So out of this, what is the weaker element? And we have to design the weaker element. So for example, if you have a pinion that is made up with cast iron, if you have a gear that is made up with steel, they have different strengths. So sigma W value for gear and pinion are going to be different, and value of y for pinion and gear is going to be different. So just by looking at those the materials, we won't be able to tell that whether gear is weaker or pinion is weaker. So when the gear and pinion are made up with different material, what we need to do is, first we have to find out out of those two, which one is weaker. And Lewis's equation must be applied. And this is something that you have to keep in mind, must be applied. Must be applied to weaker element. So which means in certain problems, you'll find your gear is weaker. So you would start designing the gear. If you see that in certain problems, if your pinion is weaker, then you will start designing the pinion. But if gear and pinion, they are made of the same material, we'll just make a statement that since gear and pinion are made up of same material, pinion is weaker, and we will design the pinion. Now, this is an important step that we have to carry out. And just for the reference, let me write it down here. Sigma W is given as sigma O, which is static, multiplied by CV. And where CV is velocity factor. So this is velocity factor. CV is not the service factor, CV is the velocity factor. And we will work out a problem step by step. Once we work out 2 or 3 problems, this process will come to you very automatically. Just for the discussion purposes, the product of sigma W, the product of sigma W multiplied by Y, this is called as the strength factor of the gear. And the reason it is called as a strength factor, because it actually sort of gives you an indication of beam strength. The next thing I want to talk about is the value of the face width, B. And you can refer to the design data book, but in design data book, usually the amount of the value of the face width will be somewhere between 9.5 times module to 12.5 times module. So this is the recommendation. So what it means is you can approximate a value of B. I mean, nobody prevented us from using 12 times M. So I can start with this approximation and then find out the value of B. So a quick note. So if you look at the equation, WT is equal to sigma W multiplied by B multiplied by pi multiplied by M multiplied by Y. So step 1, so sub-step 1 is determine whether pinion is weaker or gear is weaker. And you found out that your pinion is weaker. So let's assume that pinion is weaker. Then what we do is in step 2, WT is equal to sigma W times B pi M times Y. In this equation, we substitute sigma W is equal to sigma O multiplied by the velocity factor, and we substitute B is equal to, I'm just taking a number here, 10 times M. So now if you think about it, the left hand side of equation is known, WT is known, sigma W is known because we know the value of velocity factor. We looked at the table and found out the value of sigma O. I'm going to replace B as 10 times M, then pi multiplied by M, and we already found out the value of Y to see the strength factor, to see which one is weaker. So what it means in this entire expression, the only unknown is M. So from here, value of M can be found out. Once module is known, we know the ratio between B and M, so B can be found out. Once M is known, we know the relationship between the pitch circle diameter, PCD, is equal to number of teeth, so TP multiplied by M. So the pitch circle diameter is known. Then we know the addendum is 1 times module. So addendum is 1 times module. The value of addendum is known. Dedendum is module plus clearance, typically 1.25 times module. This is known. So which means at this stage, your preliminary gear design is done. So at this stage, preliminary gear dimensions known. Now, the only thing we don't know is this gear, whether this gear is safe under the dynamic loading, whether this gear is safe under the wear loading, and so on. So please understand, at this step, once module is known, all the major dimensions for the gear are known. And in the next step, what we need to do is we need to check this gear. So next step, which is step 2, is find dynamic load. And dynamic load is WD, which is WT that we know from the earlier equation, plus, remember this Buckingham equation, 21V BC plus WT divided by 21V plus square root of BC plus WT. And clearly we will have to find out the values of V that we know, pi d n by 60, a value of B and value of C from the tables that we referred earlier. So that is something that we need to do. And from this step, everything is known, so we can find out what is the value of WD. Once again, I just want to note here, this is the maximum possible load that could occur on gear or pinion in operation. So this is the maximum possible gear, maximum possible load that could occur on gear. And now in next step, which is step 3, we have to make sure that the static load. So next step is to check, and the only check we have is whether WS is greater than WD. This is the check, and this condition must be satisfied. So how do we do it? WS, and we have an equation for WS, which is sigma E, and the rest of the equation is same as this Lewis equation, which is B times pi times M times Y. So the only change here is this is same as step 1, same as step 1. The only difference is this is the core endurance limit, and everything is known So we will look at the tables that we talked about, and from here we will find out the value of Ws. And we have to check whether this Ws that we get from here is greater than Wd or not. And this condition must be satisfied. Now the question is, what happens if this condition is not satisfied? So here is the question. What happens if this condition is not satisfied? Now, there are some tricks that you can play here. And we will actually, when we solve the problem, we'll take a case where these conditions are not satisfied. Please understand, core endurance limit is nothing but a design specification. And this design specification depends upon the hardness, it depends upon the material. So what we can do is at this point, if this condition is not satisfied, will try to increase the value of BHN. That will automatically increase the value of sigma E. And that is very much possible for steel. Now consider we are using cast iron where you can't increase Brinell hardness number to very high value. So in that particular case, if you are stuck with cast iron, then you can manipulate the value of the face width. So what we can do is, we can either increase the design specification like Brinell hardness number. Sometimes we can change the gear material. So we can actually change the material. We will say that in this particular case, unfortunately, the low carbon steel gear does not work. So let's go with alloy steel gear. But if we are stuck, if the design requirement is that we have to design the gear in cast iron, then we have no other choice than to increase the dimension. Now here is what happens though. When we increase the dimension B, we have to go back. So please understand, when this dimension B, for some reason, if this dimension B gets increased, then there is a design iteration, because your dynamic load also has the value of B. So at that time, what we have to do is, if we decide to increase the value of B, then we have to go back, increase or find out the new value of WD, and make sure is that WS that we find, the new WS that we have, is greater than WD. Again, there is a limitation to increasing the value of B. You cannot increase the value of B to a very large value. You can't have 100, B is equal to 100 times M. That will not be a gear. That will be sort of a worm wheel. Worm. So that is not possible. So if that approach does not work, then the next approach is, we have to increase the value of M. But recognize, once we increase the value of M, we have to repeat all the steps just to make sure that the velocity factor is correct, our WD is correct, and then WS is correct. So first step is always change the design specification. If changing the design specification, like increasing the Brinell hardness number, changing the material, does not help, then we have to go back and change the geometry. The easiest parameter or geometrical parameter we can change with less number of iteration is the face width. If that does not solve the problem, then we have to go back and change the module and repeat from step 1. So assuming everything all and well, and at this point, which is the step 3, WS is greater than WD. So that condition is satisfied. So once this condition is satisfied, then we have to go to step 4. And in step 4, again, the same drill. WW has to be greater than WD. So the wear load has to be greater than dynamic load. And to find wear load, what we need to do is we have to use the equation WW is equal to dP. Please note, the wear load is always found on the pinion. WW is always on pinion times B times Q times K. And all these factors are already known. So dP is the diameter of the pinion, B is the face width, and you have the stress factor, and K is the velocity ratio factor. And we have to make sure that WW is greater than WD. And this condition has to be checked and must be satisfied. And if this condition doesn't get satisfied, then we have no other choice than to increase the value of B, or what we can do is we can play with the design specification. So K is the design specification because it depends upon sigma ES, which is the surface endurance strength, and that is how you will solve the problem. Now, step 5 is the shaft design. Is the shaft design. And it's always customary to design the shaft when we are going to design the gear. And design of shaft when we have the gear design is simple, but what I'm going to do is I'm going to give you a sort of a recipe for shaft design. And again, there are some variations which are possible. So let me give you some configurations. So for an example, you could have a shaft that is simply supported. There are two bearings, one at each end, and you have a gear at the center. Or you could have a configuration where you have the gear that is cantilever. So the gear that is sort of cantilever. And the idea is very simple. First and foremost, what we need to do is we need to find out the forces in the vertical and horizontal component. So just to recap, if you have a gear, on this gear, you have a tangential load and you have a radial load. But the actual force that is being transmitted is along the pressure angle, which is Wn. So Wt is the tangential load and this tangential load is going to make the pressure angle phi. So what we need to do is we need to find out Wn, and Wn is nothing but Wt divided by cosine phi. And from Wn, we have to find out value of Wr. Wr is equal to Wn sine phi. What that means is Wr is equal to Wt cosine of phi. So we should know the value of Wt, and we know value of Wt. Wt is equal to P divided by V multiplied by the service factor. P divided by V multiplied by service factor. Now what I want to do is I want to draw two figures. First, I'm going to show you the front view and I'm going to show you the top view. So this is front view and this is top view. So when I look at the front view, what I see is I see the radial load, WR. And when I look at the top view, I see the tangential load, WT. So I see WT. Now I'm going to show you the same thing for the cantilevered beam. So if you look at the cantilevered beam, in the front view, I'm going to see the radial load, and in the top view, I'm going to see the tangential load. Now this poses an interesting problem, which means you are going to have a bending moment diagram in the front view and a bending moment diagram in the top view. So for an example, so let me give you the steps. So for shaft design, step 1, sort of a sub-step 1, determine WT and WR. Step 2, draw configuration free body diagram. And that depends whether you have a simply supported shaft, you have cantilevered shaft, then step 3 is find maximum bending moment due to WR and find maximum bending moment due to WT. So for an example, this in our configuration is in the front view, WT is in top view. So I'm going to call this BM WR and BM WT. Now please note that these two bending moments are perpendicular to each other. So the final bending moment is going to be sort of a vector sum of bending moment because of the radial load plus bending moment because of the tangential load. This is the final bending moment. Step 4 is find the torque. And please note this torque value is known because we know the value of power. So we know, so power is equal to 2 pi nt divided by 60. So from here, I can find out the value of torque, and I need to find out T actual, which is T multiplied by the service factor. Step 5 is find equivalent torque, which means look at this shaft. This shaft is acted by simultaneous action of bending. So you have the bending moment and the torque. Both of them are acting simultaneously on the shaft. And that is because you have a gear. And we find the TEQ, and this TEQ is nothing but bending moment square plus T actual square. So bending moment we got from step 3. T actual we got from step 4. And then the last step is what we need to do is step 6 is select shaft material, the shaft material could be different than the gear material. So you could have a cast iron gear, but you could have a steel shaft. So select the shaft material, and the shaft will be always designed in torsion. So this is the fundamental equation of torsion. This equation will be replaced as TEQ divided by pi by 32 times d to the power 4 is equal to tau. This is the design. This comes from the data book, or the shaft material divided by d by 2. So from this equation, please note TEQ is known, tau design is known. The only unknown is the value of diameter, and this diameter value can be found out. So assuming solid shaft, this diameter can be found out. Last but not least, it's always a good idea to draw a neat sketch. So step 7, draw sketch of gear or pinion and show all dimensions. And when I say show all dimensions, the important dimensions are PCD, circular pitch. You should show number of teeth. So pinion, number of teeth. You should show face width. So basically, when you say sketch, we have to draw 2 views. B. And you can show addendum, you can show dedendum if you like. So this is how the gear design actually works. This process may seem involved and complicated, but please understand, this is the fundamental building block of gear design. When we follow the helical gear design, when we follow the bevel gear design, the process is going to be exactly the same. That's why we spent a lot of time on spur gear design. Spur gear design is the basis of helical gear design. What we will do is when we design the helical gear, we'll convert the helical gear into an equivalent spur gear and design that gear. So I want you to make yourself familiar with this gear design process, and I will work out the problem in next class. At this point, if there are any questions, I would be happy to answer.